Hello, everyone. The topic that we're going to be exploring for our final project is the Heisenberg Uncertainty Principle. My name is Xiong,
Hello, everyone. My name is Carlos Garcia.
And I'm Luisito Cruz.
and this is for quantum chemistry. In classical mechanics and physics, values such as position and velocity can be measured simultaneously, while in quantum chemistry, the ability to measure such values simultaneously is absent. In 1927, German physicist Werner Heisenberg published a principle that states that if we know everything about where a particle is located, then we know nothing about its momentum, and vice versa, where if we know everything about its momentum, then we know nothing about where our particle is located. In other words, this particle states that we cannot measure the position and momentum of a particle with absolute precision or certainty due to the particle's nature. Position and momentum correlate to the Heisenberg's uncertainty principle with this equation shown in white. This equation is the relationship that correlates both the position, momentum, and Planck's constant. The position of a particle is given as delta x in the equation, relating momentum and position to Planck's constant divided by 4 pi. As for the momentum of a particle, it is given as delta p. By decreasing either momentum or position, the corresponding variable will lose accuracy. This is better looked at with our images in the previous slide. The top graph shows that the position is a value that is more known, and the momentum value will be the value that we are uncertain about. This graph shows it as a wave indicating uncertainty. For the bottom graph, it shows that momentum is a value that is more known, and the position value will be the value that we are uncertain about, as shown by the wave indicating uncertainty.
So once again, these equations are essentially relating momentum to lambda, which is wavelength, or delta x, and our Planck's constant. That's equation 1. And equation 2 is relating our momentum and a position to our Planck's constant, essentially divided by 4 pi, but the h bar already incorporates 2 pi into it.
Usually, when researchers research Heisenberg Uncertainty Principle, they demonstrate this principle by having to work at a micro level, because attempting to do so with larger objects would be impossible to many variables. However, researchers from University of Colorado have demonstrated the Heisenberg Uncertainty Principle at a macro level by using a drum outfitted with mirrors, a laser, and a detector. They started by building the frame made out of silicon, with each side being 0.5 millimeters long. They then stretched out a thin film of silicon nitride over the skin to create a drum head. The drum was placed in a vacuum between two very tiny mirrors and was chilled for just around 4 degrees above absolute zero, to eliminate any type of noise. The experiment was conducted by shooting a laser at the drum head and measuring just how much the head was distorted by the photons striking it as they were bounced back and forth between the mirrors. As more photons struck the drum, the greater fluctuations have occurred in the measurements recorded, distorting the readings and proving that the Heisenberg Uncertainty Principle can be demonstrated with objects large enough to be seen with the naked eye.
The Heisenberg Uncertainty Principle relies on two qualities/characteristics. These essentially conclude that a particle not only acts as a particle but also as a wave. This is called the wave-to-particle duality, where if we look at the far left, we see an image of a particle acting as a particle, but not only a particle, also a wave, which is represented by the red. When we're talking about the Heisenberg Uncertainty Principle, relationship can be established using momentum, position, and Planck's constant divided by 4 pi, or in this case, h bar over 2, which is exactly the same thing. Now, the question remains is that are both phenomenon exhibited equally in this equation? To answer that, I've studied a little bit on this research paper paper that essentially indicates that there's an observed evolution and a free evolution, where the observed evolution relates the original equation obtained from the Heisenberg Uncertainty Principle to an equation that's obtained using different wave functions. So in the graph, the far right with the blue and the green, we have a graph establishing the particle to wave phenomenon. So in this case, we have 0.95 as being the greatest for the observed evolution, and that showcases that the particle aspect of the Heisenberg Uncertainty Principle is not equally exhibited to the wave, whereas in the free evolution section, we could see an improvement to that ratio where we have 1.00 at 2 points, which is omega and alpha. The particle to wave ratio here is 1:1, and that is with the change wave equations. So what the research was essentially summing up is that the momentum, position, and Planck's constant relationship in the Heisenberg Uncertainty Principle can be improved upon. So the 1/2 that you see currently in the equation was in the observed evolution, whereas in the free evolution, the coefficient would be somewhere near 0.418, which essentially aids in helping making the Heisenberg uncertainty relationship more accurate. More detail can be read about this research in reference 7, as shown on the next slide. Here are references, and then reference 7 is essentially telling you more about the Heisenberg uncertainty relationship and an extension. Thank you for listening to our presentation, and I hope you have a nice day.